Welcome. In this video, I'm going to be taking you on Elasticity Module 3. And under this, I'm going to be talking on two headings. And number one is force on a solid heated but not allowed to expand. And the second one, energy in a stretched wire. Now, let me start with the first one. Force on a solid heated but not allowed to expand. We know that whenever we talk of elasticity, we are talking of application of a force. But what happens when you have a solid and you apply a force and you expect in normal circumstances we expect the solid to expand or contract, but you prevent the solid from contracting and from expanding? How do you calculate the force? Now that's it. From the formula of Young modulus, we know that Young modulus equals to FL over AE, because when you rearrange, because it is stress over strain, and stress is force over area, while strain is extension over length. Rearrangement gives us this. Now, Young modulus is FL over AE. If you don't want to say stress over strain, you can say FL over AE. Now, from this formula, you can rearrange. When you rearrange, you will see that EAE was cross multiplying. AE, we multiply the Young modulus E, and it will be EAE equals to FL. I want to make my force the subject of formula, force on the solid. So divide both sides by length, divide both sides by length. Length cancel length. Now when you can rotate this, so the force now equals to EAE over length. Now, but don't forget that there's a formula that relates, we are talking about a solid heated but not allowed to expand. So this word expand as bring in expansivity. And don't forget that in the formula of expansivity, which is denoted by this, we have a change in length all over change in length all over L, change in theta. And you know, change in length in under elasticity is a extension. So if you now put extension here, that will be extension over length change in theta. So if you cross multiply this, extension will now equal to expansivity length times change in theta. So you will now come here and input the value of extension here to this place. So it now be expansivity length change in theta, then over your length. The length here cancel the length here. And finally, the force of a solid that is heated and not allowed to expand will now be force equals to EA expansivity change in theta. Keep this formula, is very, very, very important. Whenever you are calculating a force of a solid, you'll have been told in your question, they will state it clearly that a particular substance is heated and not allowed to expand. So when you hear that statement and they now ask you to calculate the force, this is the formula you are going to use. E here is representing Young modulus. E Young modulus. While the A here is representing area. While this symbol is representing expansivity. While the theta is representing temperature. So this is the formula you are going to be using. Now the length here has cancelled the length that comes from the input of our extension formula. So let's there's no length again under this formula. So whenever you are asked that what is the force of calculating force on a solid heated but not allowed to contract or expand, please put contraction here. It can contract and it can expand. To expand or contract, this is the formula. F equals to EA expansivity change in theta. You can pause the video and write it by yourself. The force on a solid heated but not allowed to expand or contract. You can write it so that you can know if you have mastered it. So the force on the solid heated but not allowed to contract or expand is this. Please don't forget, F equals to EA expansivity change in theta. Number 2. The second heading I'm going to be talking about is what I call energy in a stretched wire. Energy stored in a stretched wire. Or you can call it work done work done on this stretched wire. Don't forget that energy equals to work done. Now, how do you find the energy? Energy that is stored in the stretched wire. Don't forget that in our normal physics, work done equals to force and distance. But coming to elasticity, there's nothing like distance. Work done under elasticity is force times extension. But can you recall the formula I relate by from the formula of Young modulus, E equals to FL over AE, that I used to create and make the F the subject of the formula? As said earlier, the work done in a normal scenario is force times distance, but under elasticity, it is a force times extension. And in elasticity, let's say you stretch the wire. But by the time you place your hand on the wire without stretching it, that's force 0. But immediately you stretched it, that's the final force. So you experience a two interval of force. And in that scenario, you can have what we call the average force. So the average, the force here is average. That's why I have this half. So half F times E, and that's the first formula. This is important. This is the formula of energy stored in a wire that is stretched. Why? In other words, since F equals to KE, don't forget the relationship in the first law of Hooke's. I said force is directly proportional to extension. So you cannot replace F by KE. Oh, so once you put KE here, KE will multiply the former extension here. So it becomes square. So either you use half FE or half KE square. Mind you, the extension when force is used in the formula is not square, half FE. But when it is used with K, it is half KE square. The extension here is square, the extension here is without square. Understood.